We're going to do some periodic table trends. I'm going to zip through the first part of the PowerPoint, and then we're going to come back to it later because of the fact that I'm not here. So here we go. So take out your notebooks, get ready. If I go too fast, hey, it's a video. You can pause and always come back to it. And the best thing is the guided reading pretty much covers everything that I'm going to cover here. So definitely do the guided reading. Okay, so here we go. Periodic table trends. Lots of trends on the periodic table. We're going to learn about them. And here they come. Okay, so what the hell is a trend? A trend is general direction that something is changing or developing. So trend of things going up or things going down. And of course, there's these other things like what's trending on Google and so on and so forth. So, social media, that's cool. Okay, so next, how often do chemistry? Periodically. I know, it's funny. Okay, so what's periodic? Appearing at regular intervals. And if you look at the little vocab, or did I get these? I got it from Google. What a surprise. Relating to the periodic table and the pattern of properties that underlies it. A pattern of properties that repeats. We'll see about that in a minute. So let's check it out. Here's a bunch of patterns that you might have seen or you will see. So let's slide this up so you can see me. Here we go. So we love to graph things. We're scientists. We like to see data. It's hard to see things sometimes when there's a whole bunch of numbers. So here we have data going up. Here we have data going down. So direct correlation, reverse correlation, and here no correlation. So you get no data from that. And then when you take physics next year, distance and time, you get graphing, distance and time, distance and time. Here, x equals y, direct correlation. How coincidental. Here's a curve, exponential curve going down. We've seen this one already. This one is the curve of radioactivity. Look at that. And here we have, talking about radioactivity, the decay of carbon-14, another curve that we can get data from. And this, of course, talking about fashion. For you fashion folks, this is the height of skirts over time. So 1800s, all the way down to the ground. And then all of a sudden, look, 1927, roaring 20s. Whoa, the skirt length comes all the way up to knee length. Oh, my goodness. Oh, going back. Oh, my goodness. And then, of course, after 27, the market crashes. Everyone goes, and guess what? Length of skirts go down, too. So very interesting how fashion and money and what's going on tend to link to each other. So interesting to take a look at that. And then, of course, here we go in the 70s. Back up again, 50s conservative, and now 70s, free love, 60s and 70s, skirt comes up. And then, of course, now you got to do the finger test to make sure that you're, when it's cold now, but during the summer, you got to worry about the finger length, make sure your skirts are not too short. So there you go. So let's take a look at some trends. Here's a trend of carbon dioxide at Mauna Loa, which if you look, now we're going to see trends and periodicity here. Here is the trend. The trend of CO2 is going up. That's a trend. Global warming. It's a trend. But wait, what's this going on up and down, up and down? That's something strange. Let's take a look at it and figure out what is causing that. Closer look. Here we have goes up, goes down, goes up, goes down, goes up. Notice there is a trend. The overall trend is going up. But we notice it goes up and down, up and down, up and down. And if you look at the time, you might say, this looks to be seasonal, which makes sense because you might say, well, the trees are growing and the trees are growing, absorbing the carbon dioxide, and it's winter out now. I don't see any trees doing any green stuff. So obviously winter is affecting it. So it must be seasonal, right? Once again, look at the data. Look where the peak is. The peak is at spring, which is not what we would think. We would think that the plants would grow more down, not in the fall, but in the spring. So this is the opposite of what we would expect, which is strange. So there must be something else going on. So you stop and think for a second. Wait a minute. This is not a local issue. This is a global issue. So what's happening around the globe? Well, up here in the north in December and January and February, it's cold. But guess what? South of the equator is warm. And guess what's south of the equator? The rainforest. So the rainforest is doing its thing and absorbing the CO2 in winter or in our winter and their summer. So very interesting how looking at the data closely, you make an assumption, but what does the data tell you? The data tells you something else. So look at the data. Okay. Now we'll talk about data. This later. Stock market, stock market, stock market. Dow Jones, the wall. Statistical probability. Flattening the curve. COVID-19. We'll talk about that later. COVID-19, 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 COVID-19. Okay. Periodic properties. Save that for next week. What are periodic properties? Periodic properties are where elements in the same group have similar chemical and physical properties. So chemical and physical properties. We learned that at the beginning of the year. How coincidental. We get to see it again. Oh, could it be periodic? Oh, maybe. I don't know. Why do they have similar chemical and physical properties? Because of valence electrons. And we're going to talk about the names of the groups. We covered them a few times, but I'm going to go into juicy detail in a minute. Everyone in the first row, 1 valence electron. Everyone in the second row, 2 valence electrons. That's why we did the Lewis dots. And the noble gases have full shells, so they are not reactive, and they are gases. That's why they're the noble gases. So the reason why of the periodic properties has to do with, number 1, valence electrons. But there's something else going on too, so it's not so obvious. So, number 1, we got groups and families. Groups go up and down. Those are the vertical columns. They all have the same number of valence electrons. Everyone in the first group has 1. Everyone in the second group has 2. Skip these troublemakers in the middle. 3, 4, 5, 6, 7, and 8. 8 octet full shell. Then, as you go across the periodic table, that's a period. That is the number of shells. So this period going across, 1 shell. When we do the Bohr diagram, 1 shell, 1. Second row, 2 shells. Third row, 3 shells. Fourth row, 4 shells. So each row is a shell. So you're building shells and you're adding valence electrons. But there's also something else suspicious going on. So we'll see that in a second. 3 trends. We're going to look at the 3 trends, and then we're going to go into juicy detail. I'm going to quickly zip through them on this little video. Well, maybe I'll go through the whole thing with this video, just to zip fast through it. Atomic mass, atomic radius, electronegativity. There's a lot of trends that you can find in the periodic table. These are the ones we're paying close attention to. Atomic mass. What's the atomic mass? That's the number on the bottom that we're not spending much time looking at. That's the average mass of the isotopes. Remember we did that math? Okay, so that's the number that's on the bottom. Okay, so that is the atomic mass. If you graph the atomic mass with the atomic number, you get this beautiful line. But Mr. G, there's some things that aren't on the line. Yes, it's true. But look at that pretty line, okay? It's the best fit. It's a beautiful line, okay? Direct correlation. How nice. We love to see these direct correlations in science. Then comes atomic radius. What is the atomic radius? It is the size of an atom, or a measurement of the size of the atom. Mr. G, isn't diameter really the size of the atom? Yeah. But we measure radius. Why? Because we can't really tell how big an atom is because we don't know where the electrons are. Where are the electrons? We don't know. They're zipping around like crazy. But we can, or scientists can, measure where the nucleus is. Thank you, Mr. Rutherford. Where the nucleus is. So we know where this nucleus is. We know where this nucleus is. So using a little brain power, we say, oh, these clever people come up with these things. The distance between the two is the distance between the two nuclei, and then half of that distance is the radius. So you can have different atoms and different radiuses of the different atoms. That's how they measure. Very clever, these guys. Okay, so here's the graph. Oh my goodness. What's going on? It looks really strange. Well, there are trends and trends. Notice, just like the Mauna Loa, up and down, up and down, up and down. There is a trend going this way, and there is a periodicity of it going up and down. We'll look at that closely. Next one is electronegativity. What the heck is electronegativity? Electronegativity is when an atom wants to attract another electron when it bonds with another one. So gimme, 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 gimme. That's how you remember it. This is the official definition. I just like to think gimme, 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 gimme the electron, gimme the electron. So electronegativity is the gimme how much they want those electrons. And if you graph that, look again. We have another pattern. Looks a little different than the other one. And of course, there are exceptions here. Welcome to Honors Chemistry. We're not going to spend time on those exceptions, but just be aware that, look, there's a pattern. So periodicity, and notice a trend also going down. Interesting. So now we're going to spend a few minutes looking really closely at each of those trends and why, because we want to know why. And once we understand the why, easy. Okay, so this one's easy. Atomic mass, atomic number, more protons, more neutrons, it weighs more. Makes sense. Easy, beautiful graph. That was easy. There you go. Atomic radius. Picture's worth 1,000 words. Look at this picture. Remember this picture. This is the trend looking at a periodic table. But Mr. G, you're missing all those guys in the middle. Yeah, the troublemakers. We're ignoring those guys in the D block. Those are troublemaker transition metals. Everyone in the first row. Let's look. First row going down. Small getting bigger, 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 bigger. As you go down, the atom's getting bigger. Makes sense. It will in a minute. As you go across, the atom is getting smaller. That one doesn't make such obvious sense, but you will see why in a minute. The reasons why. Then it'll make sense. So if you have this picture in your brain, trend gets bigger going down, gets smaller going across. You have the trend in your brain, you're good, because if you know atomic radius, you know the other one, electronegativity. It's the opposite. So we'll get to that. Why? Why? Here, let's graph it. Well, it's not as pretty as that other picture, that's why, but let's take a closer look at that. Let's break it down. Break it down. Yo. Break it down. Okay, so down a group. So we're talking about going down. When we go down, it gets bigger. Well, that's obvious by the picture, right? Okay, I mean, you can tell the picture, but here's the data with the graph. So you can see as it goes down, as the atom, you go down a group, it's getting bigger, just like the picture, right? See, the picture is like the graph. How nice. Why did they do that? Let's take a look. This is why we did the Bohr diagrams. How boring. The reason why is, here you go, boink. Number one, you're adding energy levels. And atoms are like ogres. They have shells. They're like onions. So and these guys are all the guys in the first period with one valence electron. So they all have the same number of valence electrons, but look how many shells they have. Hydrogen has one shell, lithium has two, sodium has three, potassium has four, and this little bugger over here, rubidium has 5. So as you add a shell, it gets bigger. And that makes sense, doesn't it? The bigger the onion, the more shells you have. It's really cold outside. You put on a t-shirt, you put on a shirt, you put on a sweatshirt, you put on a jacket. The more layers you have, the bigger you get. And then you put on a giant sumo wrestler outfit and your giant rah, big atom. The more shells, the bigger you get. Makes sense. Yes? Yes. Doesn't that make sense? Easy. There's something else going on. What else is going on? The other reason. Come on, slide. Next reason. Went too far. The other reason going down is something called shielding, the shielding effect. Now, I use football as a great example because guess what? The defensive line defends the quarterback. They are shielding the quarterback from the other team. The more layers you have in an atom, the more shields you have. And the harder it is, the less effect there is of the nucleus to that outer electron. So the further away it is, I can't grab your cell phone from the back row, but I can grab it from the front row because all these people are shielding me in between. So reasons for up and down. Up and down, you sit down, you shut up. Sit, shells, shielding, up and down. Those are the reasons why. Don't say, oh, it's getting bigger because it's getting bigger, or it's getting bigger because it's going down. Those are not the reasons. The reasons are shells and shielding. Easy to remember. Now, going across, not so obvious. Okay, that's shells and shielding. First group, look at that. Goes up. Noble gases, goes up. Trend, yes. But let's break it down some more. Going across, it goes down. Well, look at the picture. That's why. No, that's not why. That's the visual representation of what's going on. That's what it looks like. It helps you remember. Are you going to remember the graph? Hell no. But I'm going to remember that picture. So going across, it's getting smaller. Why? Why is it getting smaller? This is why. And just to make you feel better, if you don't get it right away, it took me years, sad, I'm really slow, to understand why. So I'm going to explain it to you. As soon as the little light bulb went on in my head, I finally got it. Nuclear charge. So if you're in Mr. Evans' class, you would know ZEF, Z-E-F, net effective nuclear charge. What? What are you saying, Mr. G? Really easy. You have a shell. Period. Everyone in the first row has one shell. Everyone in the second row has two shells. The shell stays the same. You're adding an electron into that shell. When you add an electron in that shell, the shell does not get any bigger. You're just putting it in there. It's not getting bigger. But when you add an electron here, what else are you adding? You're adding a proton inside the nucleus. And the protons inside the nucleus are positive. They're attracting these negative electrons. So if you look at the picture over the little magnet, you'll see as it goes across, you're adding electrons. True. You'd think it might be getting bigger, but it's not. It's getting smaller. Why? Nuclear charge. Because when you add the electrons in the outside, it doesn't affect the size of the shell. The nucleus affects the size of the shell. So as you add a proton, the shell gets a little smaller. You add another proton, it gets smaller. You add another proton, more charge, more attraction. Another one, until you get to the end of the period, going across, the noble gases are the smallest, and not only the smallest, there's something also special about them. They have full shells, and that's going to be very important later. So as you go across, they get smaller, boom, 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 because of nuclear charge. So the reason is not because it's going across. It's because increasing nuclear charge. That is the reason across. The across reason is nuclear charge. The up and down reason is shells and shielding. Got it? Those are the reasons. And let's do a little practice to make sure you guys know how to do it, because it's going to be on the quiz. We got magnesium and Sr. Okay, let's take a look. Quick peek at them. We got magnesium over here, second group, second period, second group. Got it. Magnesium and strontium. We're going up and down. Magnesium's up here, strontium. Do I need a periodic table? It would be nice to have one, but I'll do it for you. We have someone up here and someone down here. We're going up and down. Which one's bigger? The bottom one, of course. Why? Because it's on the bottom? No. Because of up and down reason, shells and shielding. Sr has 1, 2, 3, 4, 5 shells. Magnesium has 1, 2, 3 shells. So more shells, the bigger the onion. That is why strontium, Sr, is bigger than magnesium. That's the up and down reason. More shells, more shielding. Strontium again, comparing it across with Sn, which is tin, which is way on this side. So now it's the across reason. What's the across? Well, first, which one's bigger? Strontium again, but different reason. The reason is the across reason. What's the across reason? The across reason is not shells, not shielding, not valence electrons. Nuclear charge. That's the across reason. Okay? GE and SN. GE's up here, SN is down. Up and down reason. The one at the bottom is bigger. Just think of the picture. That gives you the answer immediately. The one at the bottom is bigger, SN. But why? Shells, shielding. More shells, more shielding. Okay? Then we have GE and BR. That's going across. What's the across? Well, as it goes across, it gets smaller. What's the reason? Reason is not shells, not shielding, not valence electrons, nuclear charge. That's the across reason. Got it? So GE is bigger, BR is smaller. Gets smaller as it goes across, just like that picture that you should have in your head. Trick question. GE and F. Diagonal. Mr. G, there's no diagonal reason. Yeah, you're right. But remember the picture? Two things happening. Number one, F and GE. GE has more shells. So shells and shielding, the up and down reason, and this reason, the nuclear charge reason. So all the reasons why F is the smallest. Which element on the entire periodic table has the largest atomic radius? That would be here on the bottom in the corner. In this corner, we've got Fr, francium, with the biggest radius. But Mr. G, on that chart I looked at, it says cesium. It doesn't have francium on the bottom in that one. Yeah, I know. Sorry, the picture doesn't have the whole periodic table. It's just a mini picture so you can see it really pretty. Francium on the periodic table, use that. That's the biggest radius, the biggest of them all. In this corner is francium. Which one's the smallest? My wrestling voice. In this corner, it's helium, the smallest atomic radius. You're going diagonal again, Mr. G. Yes. Biggest down here, smallest up here. Reasons? Shells, shielding, and nuclear charge. Both. Got it? Good. Remember the picture. Up and down reason, shells and shielding. Across reason, nuclear charge. The end. Next, electronegativity. What the heck is that? Gimme, gimme, gimme. Gimme those electrons. I want electrons. Who wants the electrons the most? Well, let's take a look at a picture. Oh, gotta have the cat. Sourpuss. Favorite chemistry is electrochemistry. Graph it. There you go. Here's the data. Look at the trend. Mr. G, look at these guys over here. They're not following I told you don't look there. Stop looking at those transition metals. Hydrogen doesn't. Yeah, we'll look at him later. But look, here's fluorine in the corner. That is the biggest one of them all. Fluorine has the biggest electronegativity. But Mr. G, that was the smallest size. Yes, it's the opposite. But Mr. G, where's helium? Where'd the noble gases go? They're all gone. You're right. They are gone. Are gone. Why are they gone? Because what's electronegativity? Gimme, gimme, gimme. Do noble gases want electrons? They have full shells. They had way too much turkey for Thanksgiving. They're about to explode. They are super rich, like Pootie Pie. They got money coming out of their butts. They don't care about anybody. They don't want anybody's electrons. I'm sitting on a beach in Hawaii with $20 million. I don't need to be here. I don't need nothing. I'm just going to hang out and enjoy the sun and drink pina coladas. That's a noble gas. It's nice to be a noble gas. Everybody wants to be a noble gas. Yeah, well, at least all the elements do. No electronegativity. They don't need anything. They don't want anything. They don't want, just leave me alone. That's why they're gases. They have full shells. They're full. Leave them alone. No electronegativity. No gimme, gimme, gimmes. They don't want a gimme, gimme, gimme. They got. Here is a visual, another way, a picture of seeing it. Once again, ignore the transition metals, troublemakers. Look at the trend going across. Low to high. And fluorine is the highest, which you will get from your guided reading. Out of 4, fluorine is 4. It is the most electronegative. Fluorine is a nasty, nasty gas. So nasty, it eats rocks. It eats glass. It's nasty stuff. Very, because it really wants those electrons. It wants to be like those noble gases, which, notice they're missing. They want to be like the noble gases. They want that full shell. And they got 7. They want 1 more. They're so close to retirement. They're like 62 and a half. So close to retirement. They're like, gimme, 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 gimme. I really want that 1 electron to be just like a noble gas. So these guys really want the electrons bad. Now, notice the trend going. So here, trend going across is up, which is the opposite of atomic radius. So if you get 1, the opposite is electronegativity. Going down, size gets bigger, but electronegativity goes down. So 1 goes up, 1 goes down. You buy 1, you get 1 free. Mr. G, noble gases are missing. Yeah, true. Mr. G, why is hydrogen here? Why isn't it here where it should be? Well, once again, I told you, hydrogen, like these guys in the middle, troublemakers. Hydrogen, look where it's fitting. We'll learn about why he's there, but look at his number. He's 2.1. Based on his numbers, he should be there, but based on his electron configuration, he should be here because he's got 1 valence electron, just like helium. Helium should be over here, but guess what? When I did the Lewis dots, guess where I put it? Here with 2. So it should be here, but it's not even there at all. Why? Because it has no electronegativity. Nobody on this end has electronegativity. They're noble gases. They're literally off the chart, meaning not there. But Mr. G, I looked on a website and it says it's got point something. This is my class. It's off the chart. Next, in an off the chart negative way. So what's the trend? Trend is, as you go down, it gets smaller. Why? Don't say because it's the opposite of size. That's not the reason. The reason is the size is getting bigger. There's more shells, more shielding. Oh, there's that shells and shielding again. Oh my goodness. Look at that. Up and down, shells and shielding. There it is. Same reason. Trend, as you go across. As you go across, What's the reason? Nuclear charge. That's the reason. Yes, that is the reason. Nuclear charge. Nuclear charge is attracting. Oh, what's electronegativity? Gimme, gimme, gimme. So it's attracting. So it wants more electrons. It's attracting those electrons. And the best thing about it, which we'll get to in a minute, is that those guys, the last group, the halogens, which we're going to show you guys a little later, those guys are nonmetals. They want electrons. The metals want to give up the electrons, and we're going to learn that a little bit later. So these guys want to give electrons. These guys want to get electrons, and everybody wants to be like the noble gases. So since the noble gases are off the chart, let's do the practice. Same ones. Mr. G, you picked the same ones again. Yes, I'm lazy. I cut and paste. Same ones. Guess what? The answer is the opposite. Hello. Mg and Sr. Same ones. Which one's the greatest electronegativity? The other one. Mg. Why? What's the up and down reason? Shells shielding. Sr and Sn going across. What's the reason? Going across. Nuclear charge. Who has more electronegativity? Sn. Why? Nuclear charge. And they want the electrons. Ge. Here's Ge and Sn. Up and there you go. Up and down. What's the up and down reason? Shells shielding. Which one is the greatest? The one that's higher. The opposite of radius. Why? Shells and shielding. How about Ge and Br? That's a cross, going across. What's the across reason? Nuclear charge. Who's got the higher one? Bromine. Ge and F. Another diagonal on me, Mr. G. Yes, it is. Which one? Well, it's F. F is the biggest. Hello, out of 4, F is 4. So F is the biggest. So which element has the greatest electronegativity? I told you, F. Which element has the lowest electronegativity, excluding noble gases, which lowest, 0 is not the lowest. Lowest is on the other side of the periodic table. Fr again, who happens to be the biggest, right? The biggest size, lowest electronegativity. It's the opposite. What a coincidence. What group doesn't have electronegativity? The noble gases. Why? They don't want electrons. They have enough. They have a full shell. They have their octet. They are very happy. So, once again, doing my wrestling voice. On this end of the periodic table, we've got the one with the lowest electronegativity is francium. And on the opposite side of the table, we have what? No, not helium. These guys are off the table. They're all discounted because they don't count. Why? Because they have full shells. They don't want anything. So they are out of the competition. So who's the runner-up? Runner-up is F with the most electronegativity. Got it? Easy? Good. Here's the trends with the little arrows up and down. There's a whole bunch of them. There you go. The end.